Hello everybody and welcome back. Let's finish off our material for week 6. Here's a beautiful little snow fox. It's starting to cool down in Phoenix, and so we'll pretend that we're in the snow for a little bit. Alright, so I want to talk about second derivatives, and also we're going to talk about Taylor polynomials. Taylor polynomials are a topic that's usually covered in a second calculus class. You probably know that here at GCU, instead of having 3 semesters of calculus, we only offer 2. And so we have to take some topics out, and one of those is Taylor polynomials. But you'll need to know more about them when you get to differential equations. So I want to give you a little introduction. Plus we have a homework question that's related to that. So let's take a look. Okay, first let's start with our second derivatives though, and let's look at a Calc 1 review. Okay, so remember the first derivative tells you when the function is increasing or decreasing. So this red part of the graph, the x values for this part of the graph, and also this part of the graph are where the first derivative is positive. On the other hand, the blue part of the graph here in the center is where the first derivative is negative, because that's where the graph is decreasing, and we always read from left to right, so decreasing as we read from left to right. Let me mark this red so that we can keep track of what's what. All right, the second derivative gives us what's called concavity, and so a positive second derivative means the graph is concave up. This is the concave part of the graph here, the x values along here, and you can see they're above the graph. And let's get another color. For this part of the graph, we say that the graph is concave down because the concave part of the graph is below the graph. So that's where second derivative is negative. Okay. These 2 points, this is a relative max. That's where the first derivative changes signs. So it was positive and then it became negative. This is a relative min. Again, the first derivative changed signs there. It was negative, the graph was decreasing, and then it changed to increasing. So a first derivative changed from negative to positive. And this point in the middle is called an inflection point. And that's where the second derivative changes signs. In this case, it went from negative to positive, but it could also go from positive to negative. And inflection points are like behind the scenes, kind of warning you about changes that will happen later. So the concavity changed, but notice it wasn't much farther down the line where we had a relative min. So the inflection point is saying, okay, we're still decreasing, the function is decreasing at that place, but it's not decreasing as fast as it was. So keep your eyes open for an extremum, and in this case, a relative min comes. Okay, and also second derivative, this is the correct notation for second derivative, not the other ones, and there's a reason for that. If we have our function, d dx is notation that we use to say take the derivative of that thing. So when I'm taking the derivative of y, I put a d dx in front, and if I want a second derivative, I do it twice. So you see I have 2 d's on the top, so there's my d squared, and on the bottom I have 2 dx's, so dx squared. And it's really not squared, they're not multiplied, they are actually composed with each other. But it looks like a square because I'm composing the function with itself, or the operator with itself. And you'll learn more about operators when you get into differential equations in some of your upper level math and engineering courses. So that's that. Now let's talk about Taylor polynomials. Okay? They're used to estimate a function, and you actually learned about the first Taylor polynomial when you were in Calc 1 because the first Taylor polynomial is a tangent line. Okay? We're going to do this about a point. So we're going to pick a point in the domain of our function, and we're going to say we expand about that point. So this would be the tangent line at a point. And we're going to estimate a function at a point. Okay. The second Taylor polynomial is a quadratic. Okay, so we're going to start off with our tangent line like we did. So here's the formula that we've talked about for tangent lines this semester and the one that you've learned in your Calc 1 class. A is the point that we're expanding about. Whoops, that's a plus right there. And now I will add in a second derivative evaluated at that same point divided by 2. And I'm going to put a little exclamation point after that. We'll talk about that in a minute. Times x minus a squared. All right, that exclamation point is a factorial. So n factorial is equal to 1 times 2 times 3 times 4 all the way up to n. In this case, 2 factorial is 1 times 2. It just works out to be 2. But for example, 5 factorial is 1 times 2 times 3 times 4 times 5, and that's 120. So when you see that exclamation mark, that means that we're taking the factorial. And so that's not always equal to the number, just a coincidence that 2 factorials equal to 2. Okay? And then we can get a third one or a fourth one or whatever. This is the general form for a Taylor polynomial expanded about the point x equals a. And when we expand about 0, that's just when a is equal to 0. And that's called a Maclaurin polynomial. It's a special case of the Taylor polynomials. All right, moving along. Let's build one for sine of x, and then let's talk about why we care about this. So I'm going to get a 5th degree Taylor polynomial expanded about x equals 0. So this is actually a Maclaurin polynomial. So that's what we're going to do for this example. All right, here's how we start. We take our function, which is sine of x, because we're building up an approximation for sine of x. And we evaluate that at 0 because that's what we're expanding about. And that's sine of 0, and that's 0. Then we take our first derivative, which is cosine of x. We evaluate that at 0, or whatever point we're evaluating at. In this case, we're using 0. We'll take our second derivative, which is minus sine of x, evaluate that at 0. We'll take our third derivative, which is negative cosine of x, evaluate that at 0. And our fourth derivative, which will be negative sine of x. And, whoops, there's a prime, a double prime, a triple prime. Here's my fourth derivative. Is sine of 0, which is 0. And we're taking the 5th degree, so I need to go one more. So here's my 5th derivative, which is cosine of x. I'll evaluate that at 0. And that's a 1. Okay? Now I'm going to start to build my polynomial. I'm going to start off with 0 plus 1 times x minus 0 plus 0 over 2 factorial times x minus 0 squared plus minus 1 over 3 factorial times x minus 0 cubed, and so forth. The next one is a 0. I'm running out of space, so I'll just leave that out. And then the next one is plus a 1 over 5 factorial times x minus 0 to the 5th. And when I clean this up, I'm going to get x minus 1/6, 3 factorials equal to 6, x cubed, plus 1 over 120, x to the 5th. So this was my 3 factorial, and this was my 5 factorial when I clean that up. Now here's why we care about this, especially you computer science guys, but everybody. You're going to have to be doing some programming in your programs. All right. Computers cannot take the sign of x. Computers can only add, subtract, multiply, and divide, and they do that by moving all those ones and zeros around. Okay, they do that in assembly language just by moving things to different memories, and that's really all they can do is add, subtract, multiply, divide. That's what polynomials do. They add, subtract, multiply, and divide. So let's take a look. I'm going to open up Desmos, hopefully soon. I'll pause while we're waiting. Here it comes, never mind. And let's graph sine of x. So there's our sine of x. Okay. There's my tangent line. That's if I stop at the first term of my polynomial, right there, x. Let's put in a minus a 1/6 x cubed. And look what I get. I have a cubic, and notice now it's a much better approximation to the sine of x. Let's put in our next term that came out not to be 0, which was 1/20th over x to the 5th. Let me actually just put 1 over 5 factorial, if I can find there it is, x to the 5th. Bingo, there's that. Look at that. It expands a little bit farther. I have a little bit longer and better approximation. Let's go a couple more. The next term works out to be 1 over 7 factorial, x to the 7th. You can see I get a better approximation, plus 1 over 9 factorial, x to the 9th. And I can keep going and going and going. And each time I do this, I get something that's a little bit closer to the sine of x. And not only is it a little bit closer, it's closer for a wider range of values than I had before. So I can use a computer. I can add, subtract, multiply, or divide to get an approximation of a trig function. And that's actually how your calculator calculates these values. It has Taylor polynomials built into it to evaluate square roots, logarithms, trig functions, anything else that's not a polynomial. Okay, so that's why we should care. Moving on. Now let's talk about partial derivatives and how we get our second notation. I have an example up here of the sine of x times y squared. And we can actually get 4 different partial derivatives. Okay, the notation here goes in order. This says take the derivative with respect to x and then with respect to x. And my notation here, look, it looks a lot like the second derivative notation we had before, except for the fact, of course, we have the curly derivatives instead of the straight d's on this. Okay, let me erase that circle. And let's get some more inking. Okay, fyy, of course, we take with respect to y twice. Here, fxy, we do x first and then y second. So when you see the notation with the function, you're going to read left to right. But when you see the notation as a fraction with what's called the Leibniz notation, we read from right to left, and that's because we're applying that derivative. So z is my dependent variable. I first take the derivative with respect to x, And after I take that derivative, I take the derivative with respect to y. So that's why it's in that order, because I'm applying those derivatives the way we talked about earlier. Okay, and then the notation for the other one. So let's calculate a few of these. Let's see, I'm going to do some erasing, get some of this out of the way because these do tend to take up some space. So let me erase all this. And let me erase that. And I'll get some ink back. And now let's see. So f sub x is going to be cosine of xy squared times the derivative of xy squared with respect to x, which will be y squared. F sub y will be cosine of xy squared. I'm using a chain rule. Times the derivative of xy squared with respect to y, which will give me a 2xy. Now if I want fxx, I'm going to take the derivative of fx with respect to x. So in that case, the y squared acts like a constant, so it'll carry along. And I'll have the derivative of cosine, which is negative sine. Let me erase that cosine that I started to write. So I'll have a negative sine of xy squared. And again, I take the derivative of xy squared, and I take that with respect to x, so that'll be another y squared. So that's negative y to the fourth times sine of xy squared. fxy, I take the derivative of fx with respect to y. And now I have a product rule, because I have a y on the outside and a y on the inside, so I'll use a product rule. So the derivative of the first times the second left alone plus the first left alone times the derivative of the second, which is negative sine of xy squared, times the derivative of that, which is 2xy. And let's clean that up. So I'll have a 2y cosine xy squared minus a 2xy cubed times sine of xy squared. And then I can do the same thing for f sub y. I won't do them all. Let me do f sub yx. So we could do f sub y. That would take a product rule because I have a y on the outside and a y on the inside. But let's do f sub xy. Yes. No, yx. I'm so sorry. The y comes first and then the x when I use the subscripts. So again, that takes a product rule. I've already taken the derivative with respect to y, so now I need the derivative of that with respect to x. So another product rule. So the derivative of the first times the second left alone plus the first left alone times the derivative of the second, which is negative sine of xy squared, times, let's see, the derivative with respect to x of that will be y squared. And that all works out to be 2y cosine xy squared minus 2xy cubed times sine of xy squared. I got the same thing for that. I wonder if that happens in general. The answer is yes, it does. Okay, so when I have, these are called mixed partials when I take the derivative with respect to two different variables. When I have mixed partials, it doesn't matter what order I take them, I will get the same answer. So we can leverage this. Okay, here's an example down here. Suppose I wanted to find fxy of xy, of this function. down here. It's a mess. Look at that. X squared, 3x cubed under a square root. I've got a log in the denominator. It's a mess. If I do it this way, this says take fx first, then take, let me write ddx, then take ddy. And ddx is going to be a mess, but I can turn this around. To take fyx, and that says take the derivative with respect to y first. Well, when I do that, this stuff all goes to 0. And so all I have to do is take the derivative of that, and so I'm going to get 0 plus 6xy. And there's my answer right there. So we can leverage that in that case. All right, moving on. There are extensions to Taylor polynomials when you have more than 2 variables. All right, around it, again, we're going to do it around a point like we did. Okay. And again, the first Taylor polynomial is just the tangent plane. Since we have 2 input variables, we don't have a tangent line anymore, we have a tangent plane. So the first Taylor polynomial is the tangent plane, which happens to be, there's my tangent plane. And then for my second Taylor polynomial, I add this stuff along the bottom. So let's take a look and see what this is. Well, let me keep that notation and come back to this from my current slide. Don't do that. So let's see what we have. We have the second partial with respect to x times x minus a squared times a half. We have the second partial with respect to y times y minus b squared. Remember, that's the point, times a half. And we have in the middle the mixed partial times x minus a times y minus b. Okay, that's just a formula. Just know it. Actually, it won't be on the test. Just know it for homework. So let's look at an example. We're going to find the quadratic. Quadratic because I have quadratics. Second degree is my highest degree. Quadratic Taylor polynomial about 0, 0. So that's my a and that's my b. And my function is z equals e to the negative 2x squared minus y squared. So what do I need? I need my first partial with respect to x, my first partial with respect to y. I need my second partial with respect to xx, my second mixed partial, and my second partial with respect to y. So I'm just going to go ahead and find those. I don't want to use red, I'm going to use black. So my f sub x, I'll find my f sub y over here. The f sub x is going to be e to the minus 2x squared minus y squared times negative 4x. My f sub y is going to be e to the negative 2x squared minus y squared times negative 2y. My fxx is going to be, I need a product rule. Let me rewrite my fx, minus 4x e to the minus 2x squared minus y squared. So my fxx, I'll use a product rule. Negative 4 times e to the minus 2x squared minus y squared plus a minus 4x times e to the minus 2x squared minus y squared times the derivative of that exponent, which will be a negative 4x. So that'll make that, and I'll just put a square there. For fyy, let me rewrite it again. I like that polynomial in front of the exponential. It's not necessary, it's just easier for me to see. So again, I'm going to take a product rule. So fyy is going to be the derivative of the first times the second left alone, plus the first left alone times the derivative of the second, which is e to the minus 2x squared minus y squared times its derivative, which will be a negative 2y, so that'll just make that 2y squared. And I also need an fxy or fyx. They're both equally easy, so I'll find fxy. And let's see, so that means the derivative with respect to y, so the negative 4x will carry. And I'll have e to the minus 2x squared minus y squared times minus 2y. And so that becomes a plus 8xy times e to the minus 2x squared minus y squared. Whew, that's a lot of pieces. Did I put on another slide to help with this? No, I didn't, unfortunately. All right, so the next thing I do is I evaluate these things at my point A, B. So I've already calculated them. Now I will evaluate them. So f sub x works out to be 0 when I plug in. F sub xx works out to be minus 4 when I plug in. fxy works out to be 0. Thank goodness. Fy works out to be 0, and fyy works out to be minus 2. So now I can begin to evaluate this. Okay? I need the function evaluated at the point. Oh, let me go ahead and do that too. That's a 1. Okay. So I need the function evaluated at the point. That's a 1. Plus the first partial times x minus 0, because my a is a 0. Well, the first partial is a 0, so I have a 0x. Plus the first partial at y evaluated at y minus 0. That was a 0. Plus 1/2 the second partial with respect to x times x minus 0 squared. There's a minus 4. Plus the mixed partial, which was a 0, plus 1/2 the second partial with respect to y, which is a negative 2, times y minus 0 squared. So my Taylor works out to be 1 minus 2x squared minus y squared. All that work just for that. Let's look at a picture in GeoGebra. Keep my ink. We'll open up GeoGebra 3D. Let's put our original function in, which was e to the minus 2x squared minus y squared. So there's our function. That's what we want to evaluate. Our tangent plane was just the first part, 1 plus 0x plus 0y. So there's our tangent plane. We move it up. Sure enough, looks tangent to me. And our second Taylor polynomial was 1 minus 2x squared minus y squared. And so that purple is our second Taylor polynomial. And you can see, again, it's still tangent, but you can see because of that curve, it fits our original exponential curve a little bit more nicely. And if we went on to a third Taylor expansion and fourth and so forth, we would get functions that would fit more nicely again and again, just like we did for the Taylor polynomials in one variable. Okay. You have 2 homework questions that ask you to do this. Like I said, it won't be on your exams at all, but you do need to know this when you get to differential equations. I'm sure he'll go over it again, but I wanted to put this in your brain so that at least when you see it, it's not one more brand new thing when you get to differential equations. And then finally, if you want to work with this inside of inside of Mathematica, here's some script for you so you can take a look at that. I'll have this up online for y'all too. So thanks very much. Looking forward to seeing you in class this week. Take care. Bye-bye.